as this, it's just equivalent to integrating 3 all over x squared minus 1 all over x plus 2 with respect to dx. Do you understand this, yeah? Okay. So what you can do is you can integrate 3 all over x squared with respect to dx minus, and then you integrate 1 all over x plus 2 with respect to dx. Do you understand? So you just split it up into two separate integrals. Does that make sense? Okay. So instead of writing 3 all over x squared, you would have 3 x to the power of minus 2, like this. So if you just think about what would happen if you were to integrate that, or you just add 1 to the power and divide it by minus 1. Okay? And then for this, it's basically like reverse chain rule. So if you were to think, okay, if I integrate 1 over x, it's natural log of x, right? Plus c. But just forget about the plus c. It's just natural log of x. So we're going to guess. We're going to make a guess. We're going to say, let's consider the integral of this. Let's guess that it's natural log of x plus 2. Does that make sense, yeah? So we're going to make that guess. So then if we try and find the derivative, it will be 1 all over x plus 2 multiplied by the derivative of x plus 2, which is just 1. So notice it is exactly that. Does that make sense? Okay, does this make sense, what I've done here? So the answer to the first part is this, the answer to the second part of the integral should be that. Integrate 3 all over x squared. So you write that as 3x to the power of minus 2. So you're just adding the power by 1 and then dividing it by whatever that new power is. Does that make sense? Actually, you know what? So this would just become minus 3 all over 4 minus 3 all over 2 minus natural log of 4 plus 2 minus natural log of 2 plus 2. Because those are the limits. I'm looking at both of these separately. Three over 2, and you've got natural log of 6 minus natural log of 4. So then your answer will literally just become 3 over 2 minus natural log of 6 over 4. Rule of logs, you're subtracting 2 logs, so you divide 6 and 4. So your answer should just be 3 over 2 minus natural log of, what would that be? 3 over 2 also. Give me a sec, let me just check if that's correct. Hang on a second. No, something's off. What's wrong? Minus 3/4 plus 3 over 2. Minus 3/4 plus 3 over 2. Okay, I've made 2 stupid mistakes. Okay. Now, sorry. You've got 3 over 2 minus 3/4. That should be 3 over 4. Because this is just the same thing as 6 over 4. That should be 3/4. And then for this, I've made a... No. The second part was actually correct. So it is 3/4 minus natural log of 3 over 2. Or you could write as 3/4 plus natural log of 2/3 if you wanted. Doesn't make a difference. Okay. Do you have any questions on that? Yeah. Do you have any other questions you want me to go over? (11G), any other questions in the textbook? Mm-hmm. Okay. You did part A? Okay. So, did you use your answer to part A to help you with part B or no? So that's probably why you couldn't do the question. You should appreciate that you can use this bit of information to help you here. But you didn't do that, did you? No, 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 no. So the whole point here is they're asking you to use integration by parts. Let me just write down the answer to part A here. So when you integrate this, you'll get that's equal to minus 2/3 of 8 minus x to the power of 3/2. So it's like they've just used reverse chain rule. Okay. Now, when you do part B, the first question you're going to ask yourself is, what are you going to set to be u? So would it be u is equal to x minus 2 or u is equal to square root of 8 minus x? So let's have a think about this. If you're stuck on part B, you need to remember in your exam, if you ever get stuck on a question, make sure you use the previous part of the question to help you, because it's definitely going to be helpful. So what does part A tell us? Well, part A tells us if we integrate 8 minus x, we're going to get this. So basically, it's like, imagine this was some derivative, right? dy over dx. If you integrate this derivative, you're going to go back to y, right? And if you think about how you do integration by parts, you set one thing to be, what's it called? U and then dv, and then you, yeah, let me just double check this. It's been a while since I've done this. Yeah, so you have u dv over dx, okay. So look at this. You're going to set one of these to be u. You're going to set one of these to be dv over dx, right? So what's going to happen with u? Well, you need to find the derivative, right? But the truth here is, what did I do in part A? Well, I was integrating this expression, right? I was integrating this expression. This cannot be u, because notice we're differentiating it, right? But notice in part A, we integrated it. Here we integrated this, but here we're differentiating. So we can't use part A, right? So so it doesn't make sense. It doesn't make sense to set u to be equal to square root of 8 minus x. Does that make sense? Hello? Yeah. In part A, you're integrating this expression, square root of 8 minus x. So you're asking yourself the question of, you know your two functions are x minus 2, root 8 minus x. That looks familiar. But then here, it's like, okay, do I want to differentiate this expression when doing parts or integrate it, right? So that depends on which one you set to be u or v. So if you look at square root of 8 minus x, and if you were to ask yourself, okay, well, I want to integrate it because then I can use part A, right? Do you understand? But the thing is, if you look at setting it to u here, I would have to differentiate it. So u should not be set equal to root 8 minus x because that wouldn't let me use part A. Instead, if I was to say, well, let dv over dx equal root 8 minus x, I need to find what v is, you know? And in order to do that, I need to integrate this expression. You understand? And then I can use part A. Yeah. 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 Main point here is you want to use your answer to part A, right? So you want to be integrating either x minus 2 or 8 minus x, square root of 8 minus x. So the question is, which one do I want to integrate? Well, I want to integrate the second term. So if I did set it to u, I wouldn't be able to do that. So that's why we don't do that. So we set u equal to x minus 2, and dv over dx is equal to square root of 8 minus x. So then to find v, then you just have to integrate that. And notice we don't need to work this out because we can just use what you've put to part A. Does that make sense? Okay. Of course, with u, because that's x minus 2, very nice. And very fortunately, we know what the derivative will be. It will just be 1. So if we use the formula for integration by parts, I never really write down the formula, but I will here. So you got u, which is x minus 2, and then that's being multiplied by v. Now we know that v will be equal to minus 2/3 of 8 minus x power of 3 over 2. Does that make sense, what I've done there? Yeah. Okay, and then you're going to subtract that by v, which is just going to be the same thing again. Minus 2/3 of 8 minus x power of 3 over 2. And then you're going to multiply that by du over dx, which is just 1. Very lucky there. So then, before I do try and simplify this, you want to figure out what is this integral. And of course, it's not a very nice integral. So you got minus 2/3 of 8 minus x to the power of 3 over 2 with respect to dx. So we want to integrate that. Let's just bring the minus 2/3 out. So then you ask yourself this question. Okay, I want to integrate this. So if I was to integrate this, well, that looks like there's subtle hints of a reverse chain rule here, right? So what we can do is we can make a guess. Well, this looks like something to the power of 3 over 2. And because of that, I can say, well, I can make a guess. When you integrate something, the power should go up by 1, right? So you can say, well, let my guess be, well, let y equal 8 minus x to the power of 5 over 2. Well done, yeah. So then let's try and find the derivative of that and see if there's any match or mismatch. So you would have 5 over 2 times 8 minus x to the power of 3 over 2 times minus 1. Yeah, well, we're kind of past that now, but yeah, pretty much this is it, yeah. So then remember, the thing that we want is we just want 8 minus x to the power of 3 over 2. We've got minus 2.5 times that. So all we have to do now is just divide it by minus 2.5, or minus 5 over 2, I should just say, right? So that means, well, I should divide the original thing that I considered by minus 5 over 2 also. So the answer to this integral should be minus 2/5 8 minus x to the power of 5 over 2. The reason why it's minus 2 over 5 is because when you divide by a fraction, well, you have to flip the fraction, and you're just timesing it by that. Do you have any questions on that? So then we know that this whole thing will just be, so then you would have minus 2/3 multiplied by minus 2/5 8 minus x to the power of 5 over 2. So then you would have 4 all over 15 times 8 minus x to the power of 5 over 2. Okay? Now, that's the most difficult part done. Because now from this point forward, we can just put that back into this. We figured out that integral, so now we have x minus 2. One thing that I can definitely, actually, no, I can't do that yet. Now I can put that back in, so you got minus 4 over 15, 8 minus x, 5 over 2. Let me just see how I'm progressing. Something does look a bit weird. So we want to, I don't know, we'll see. There's only one term here, so I'm not sure how I'm going to merge it in the end. Okay, we'll figure this out. Notice this is only one singular term, but we don't have that here, right? So we'll see how we're going to navigate around that. I already have an idea, but I'm not too sure. So one thing that you can start doing is, well, basically tidying up this expression. So you got minus 2/3 into x minus 2 into 8 minus x to the power of 3 over 2 minus 4 over 15, 8 minus x, 5 over 2, and then we'll put a plus c. Now, this is what we've gotten to. We can't really do anything. We can't do much more at this point. All right? We know that we've got two terms, but then if you look at what they want, it's only one singular term, right? But if you look very carefully, you can do something quite smart. You can factorize. Yeah, you can factorize out 8 minus x to the power of 3 over 2. So if you do that, so you got 8 minus x to the power of 3 over 2. So the first term will become minus 2/3 into x minus 2. And then you've got minus 4 over 15, and then 8 minus x. And then you've got plus c. So we're just factorizing the first two. Do you have any questions on this so far? It's tricky to figure out that you factorize that, but I've noticed in the exam that they're expecting students to know how to do this. So just bear this in mind. So now all you have to do is just expand and simplify. So you got minus 2/3 of x plus 4/3 minus, I don't know what that would be. That would be minus 32 over 15 plus 4/15 of x plus c. I wonder if this fits together nicely. minus 2/3 plus 4 over 15 gives me 1. Well, that's minus 10 all over 15 plus 4/15. That's minus 6 over 15. So that's minus 6 over 15x. Then you've got 4/3. That will be 20 over 15 minus 32 over 15. Minus 12 over 15. Is that's not what's given? Yeah. Interesting. They've got minus 2 over 5 on the front. So yeah, that's one difference. That's one of the other differences. They've got minus 2 over 5 here. So let's see what happens if we do take out a factor of minus 2 over 5. Do we get that? If you take out a factor of 5 first, that's interesting. 2 over 5 times what gives you 6 over 15? So let's do that. So 6 over 15 divided by 2 over 5. That's 6 over 15 times 5 over 2. That will be 30 over 30. Oh, that's nice, yeah. So if you take out 2/5, then you would get minus x. Yeah, I mean, if you take out minus 2/5, then you'll just get x. And then if you do 12 over 15 divided by 2/5 also, I'm pretty sure you'll get something similar. So then you would have 12 times 5 all over 15 times 2. So that's 60 divided by 3, which is 6. So, do you have any questions on that? So that last step is a bit tricky because that might throw you off a little bit. But if you look very carefully, they took out that factor of 2/5. So the important thing is you just divide. So what I did was I just divided this and this by 2/5. Well, I should say negative 2/5. And then that led me to getting not x plus 6, x plus 2. Yeah, it's not easy. Yeah, it's a very tricky question. Okay, and then I'm not going to go through part C because it's just substituting the same expressions in. Any other questions? Mm-hmm. 11E, question 9. Oh, did you try this question? Okay. Now, just heads up. In the exam, they usually tell you which substitutions to use. Usually. When I did it, that's what they've done. I don't know if they've changed it now, where you have to figure out which substitutions to use. But if they did that, that would be very cruel. In the textbook, I'll check in the exam questions because in the exam they usually always give you which substitution to use, so they're not that cruel, hopefully. But I mean, if they wanted, then yeah, they could put a question like this. One thing I want you to pay attention to with this question is when you look at this expression, it's most likely going to be either one of the three substitutions, and you can probably think why. So it's either sine, it's either cosine, and it's either actually it could be 4. It could be tan, or it could be actually no, sorry, could it be tan? 1 plus tan squared is sec squared. Yeah. Well, actually, no. It could be. It's probably sec. Now, why did these three pop up in my mind? Why do you think? Look at the underlying structure of this. Look at the underlying structure. Look at how it's built. Yes. Look how it's built up. More than just that. It's more than just that. Pay attention to the second. But there's more. What else? Remember when we were doing those differentiation questions with the trig functions? Give dy over dx in terms of x, and you had to use a bunch of trig identities. My point being is, yes, there's a bunch of squares, but this is very similar to. That's what I was trying to get at. And you can even argue for sec. 1 plus tan squared is sec. So you could just rearrange it like this. Do you see my point now? That's yeah. Question is, which one do you use? That's a tricky one. One of the things that I'm going to do is no. You know what? Actually, that's a viable strategy. Yeah, you could use trial and error. What I was thinking is, yeah, I mean, at worst case, I think trial and error is probably the best way to approach this. I'm just thinking, is there a way that we can use without? Is there an alternative method that we can use rather than go for trial and error? Why would sec not work? Well, you know what? Screw it. Let's just use trial and error. Why not? But we're not going to use. All we're going to do is we're going to see what would happen in each scenario. So if we had x is equal to sine theta, then you would have the integral of sine squared theta times cosine of theta, right? With respect to d theta. That looks solvable. That looks very solvable. If you look at the second one, well, then it's just similar. It's cosine squared, but this time it's just times sine of theta. Again, that's solvable. We either option can suffice here. So we could actually, so straight up, we could use either one of these. Notice one thing. Notice I'm not actually solving. I'm just checking if the integral looks solvable. So that's really important to note there as well. If you have x is equal to sec theta, let's check if that's solvable. So you would have sec squared theta tan theta. You know what? That is solvable as well. And you may think, why? Do you know what all three of these questions have in common? This is a very nice question. Well, it's deeper than that. There's something deeper than that. Mm-hmm. I'll show you anyways. What do you notice? Look at the third one especially as well. What do you notice? What's the relationship between these? Yeah, but we're already doing that. There's something more. Basically, my question is, why are these integrals? Why can we definitely solve them? How do I know that these are not hard integrals? That there's actually analytical solutions to them? Like you can actually figure these out. How do I know that I can figure these out? No? So just to let you know now, if you choose any of these three functions, yeah, it doesn't matter. So you basically choose any three. By the way, if you were to use, for example, tan or cosec or cot, I think you would basically have integrals you wouldn't be able to solve. Potentially. So you have to think about which. So before I tell you the answer to this question, one of the things I just want you to want you to realize, is based on the underlying structure of the integral. So based on the underlying structure of the integral, and what I mean by that is it made up of what do you call it? Fractions, powers. Um, square roots. So based on that, and 1 second, let me make this a list. So that's the first thing that you think about. So is it made up of these? The other thing that you have to ask yourself is, what is the order? Is the order of the operations, and do they have? There's a special word for this, so it's not coming to me. Do they have a similarity to any trigonometric identities that you know of? So those are the three questions that I was asking myself. Oh goodness me! So that's one thing I just want to put out there. Okay. What are the order operations? So, for example, if I told you, okay, it was made up of fractions and powers, is it like a squared over b squared, or is it like, oh, actually, no, that's a bad one. Okay, is it like, actually, let me think of this. Say if you have like 2 plus 3 times 5, it could be like 2 times 3 plus 5. So the whole point here is the operators are in different order. So the order of these operations matters. Is the times coming first or the plus coming first? What's coming after the other? So for example, like if I had x squared minus 1 rather than 1 minus x squared or something, then, that would influence your decision on, which trig identity that you could use. Do you understand what I'm saying? So that's pretty much it. Back to my original question: why can I solve these integrals? Do you want to have another? You want to have another crack at it? What's the relationship between these and these? When I tell you the answer, you'll be like, "My goodness, how did I not think of this?" You're nearly there. Not inverse. You're thinking along the right lines. Yes. The derivative of tan is what? No, it's sec squared. You need to start memorizing these. So that's telling me that you're not practicing enough differentiation. You need to practice enough differentiation to get to a point where you memorize these. And that's common in all of these. Why are all of these solvable? You can just use a reverse chain rule for any of these. Okay? They basically follow. Remember, I talked about integration by inspection. Or I called it by inspection, right? I should really say that as well. Remember, if you have anything in this form, it is in the textbook, where you have the derivative multiplied by the actual function itself, then you can safely assume, well, let's say if this was n. So you've got some function to the power of n, right? Times by some derivative. Then you can basically assume your answer might be in the form of f of x to the power of n plus 1. So, yeah. Okay, so let me go through this. Choose one. Which one do you want me to solve? Okay. So first things first, what I'm going to do is I'm going to rewrite this in a way where it's more clear. You understand this? Yeah, same thing. So this is like f of x, this is like f prime x. So what we can do is we can say, basically let's consider the answer being not sine squared, it's not sine theta squared, but sine theta cubed. Let's consider that. So if we were to actually find the derivative, or what would end up happening, you'd have 3 sine squared theta, and then you multiply that by the derivative of sine, which is cosine. Does that make sense? So, look at that. Look at the thing that we're trying to integrate. Sine squared theta times cosine theta. That's what we've got here. The only difference is we just have to divide this by a factor of 3. So your answer to this would be a third sine cubed theta. Does that make sense? Now, if in the event I had sec squared theta tan theta with respect to d theta, like this, this is f prime x, this is f of x, okay? So how would I apply the same instance here? This one's a lot more tricky, because one thing that people won't acknowledge is this is to the power of 1, right? So you would actually consider, you would say, well, let's consider y being equal to, not tan to the power of 1, but tan squared theta. This one's incredibly tricky to look at. But do you see that? Yeah? So you always consider 1 power higher when you've got this instance where you've got the derivative times by the actual function. When you've got those two things multiplied with each other and you're integrating it, then you have to consider 1 power higher of the original function. That's how this works. Okay? So if we consider tan squared theta, let's try and differentiate it. So you've got 2 tan theta times tan theta. Sorry, times by the derivative of tan theta, which is sec squared theta. Does that make sense? So then here, you would just have to divide it by a factor of 2. So your answer here would be half tan squared theta. Does that make sense? They are different, aren't they? A third sine cubed theta, half tan squared theta. They are different, aren't they? But I guarantee you, 100%, with one thing that I should probably put is a plus c. Depending on the plus c, these expressions will be equivalent in some way, shape, or form. They're not exactly equivalent, but depending on plus c, they can be equivalent. So it may feel a bit strange to get different trig functions, but I can safely say this is perfectly normal. Some integrals can be expressed in one form or another. Okay? But for the sake of simplicity, let's just stick with the third sine cubed theta. So, I just realized we technically did solve this integral just now. We didn't substitute the limits in. So with this question, we said x, so let's use x is equal to sine theta, basically. So if you've got x is equal to sine theta, root 3 over 2, that's when, how do you call it now? Theta will be 60 degrees, or basically pi over 3 radians. And then when it's a half, it's pi over 6. So then the integral that we were just solving now, oh my goodness, I just realized something. Oh my goodness. Okay, I'm so sorry. I forgot to do one very important thing. Can you guess? Work this out now. damn it. Okay. I think majority of that is wrong. The dx. So when you change it into d theta, you're going to get another function, basically. It may be... So basically, you see these integrals I was considering, these were still in dx without me realizing. But I need to change these limits. So if I said x was sine theta, so you would have dx over d theta is equal to cosine theta. So then dx would be equal to cosine theta d theta. So there should be another cosine theta here. You understand? So that's one thing I just realized. Okay, but actually, you know what? I'm kind of glad that happened because hopefully you can. Well, no, it will change it quite a lot. But hopefully, by generating these examples, I just want you to realize the importance of the reverse chain rule. Okay, but you're happy with the integrals that I was solving, right? I guess it was a bit of a detour. Okay. So one of the things I will just, let me rub some of this out. Okay. Yeah, so let's choose x is equal to sine theta. So by the way, it doesn't matter which one you choose, because theoretically speaking, all of these make sense, you know? All of these actually, they fit the underlying structure of the integral. So if you've got x is equal to sine theta, well, let's substitute that in. So first of all, if x is equal to root 3 over 2, we know that theta will be pi over 3. If x is equal to a half, we know that theta is pi over 6. If you've got x is equal to sine theta, we know that dx over d theta is cosine of theta. So we know that dx can be written as cosine theta d theta. So then, yeah. So then what we can do with this is we can say, well, we're just solving the integral of pi over 3, between pi over 3, pi over 6. You've got x squared, so that's sine squared theta times cosine of theta. Actually, you know what? Let me not write like that. And then remember, we need to substitute the new limit. So instead of dx, we're going to write cosine theta d theta. Okay? And in this question, or in this case, it's not a nice integral to solve. I'll be honest with you. This is a very horrific integral. But it's still solvable. Okay. Let me show you how to solve this integral. You're not going to like this at all. Really not. You've got sine squared theta, cosine squared theta. So what you can do is you can write as sine theta times cosine of theta, all squared. Yeah. Now, I just want you to develop, you'll get so good at trig functions and trig identities, you'll realize when you've got the product of sine and cosine, your mind should just jump to the formula for sine 2 theta. So whenever you've got a product of a sine and a cosine, your mind should jump to the double angle formula for sine 2 theta. Does that make sense? So then effectively, I can write this as a half of sine 2 theta. Yeah. So then you get a quarter sine squared 2 theta. Now you're probably thinking, well, this doesn't help me either because I still have to integrate this. But you know, this is kind of funny. But whenever you've got a sine squared, whenever you're trying to integrate a sine or cosine squared, so whenever you've got sine squared or cosine squared and you need to integrate that, what do you do? use cosine 2 theta. Because you know that cosine 2 theta, in this case, is 1 minus 2 sine squared theta. So then notice you can write sine squared theta as 1 minus cosine 2 theta all over 2. Do you understand that? If I asked you straight up, can you integrate sine squared theta? Would you be able to do it? If I was to ask you, okay, would you rather integrate this, or would you rather integrate this? Which one looks more easier to deal with? Exactly. You can actually integrate the second one. Well, the first one you can't. Why? Because I actually use the trig identity there. So whenever you've got a sine squared or a cosine squared and you can't integrate it, you use cosine 2 theta, you use a double angle formula for cosine. But then if you've got a product of a sine and a cosine, then you use sine 2 theta. Does that make sense? Yeah. It's like a hint. Okay. So then you've got sine squared of 2 theta. What we can do now is we can write this as pi over 3, pi over 6, and then you have a quarter, then 1 minus cosine of 4 theta, all divided by 2 with respect to d theta. Do you have any questions on that? Do you understand what I've done there? Yeah. So then, from this point onwards, got pi over 3, pi over 6. So you got a quarter times a half, which is an eighth. Yeah, so you got an eighth all around. Actually, what I'm going to do is I'm going to bring out this factor of an eighth. So no one likes fractions, let's be honest. So you got an eighth, and you got 1 minus cosine of 4 theta with respect to d theta. Now, just to kind of save some time, if you were to integrate this, you'll get theta minus a quarter sine 4 theta. Pi over 3, pi over 6. Okay? And then you just substitute the limits, and then you get your answer. That's it. Yeah, I know it's not easy. Pi over 6 minus a quarter sine 4 pi over 6. That's 2 pi over 3. 2 pi over 3 is 150. That should be equal to a half if I remember correctly. Actually, you know what? Screw this. You can just type it into your calculator, right? Of course, just do that. Don't what I'm doing. So if you do all of this, you should get your answer to be 2 pi plus 3 root 3 all over 96, apparently. Yeah. So just as a heads up, they will usually tell you your substitution. Usually. I've never seen an exam question where they don't. So just watch out. If they don't tell you, look at the underlying structure. You get square root 1 minus x squared. That looks very familiar to these identities. They look pretty much the same. So, yeah. Do you have any other questions? I just realized something. You can't use sec. Or you can, but you can't. Because if you look at sec and you rearrange the formula, notice it's square root of sec squared theta minus 1. So that's square root of x squared minus 1. This is actually a really important thing to point out, because notice this 1 minus x squared. So say if the question was square root of x squared minus 1, then you probably want to use tan as a substitution. Well, not tan, sec as a substitution. Does that make sense? I thought I should point that out. That's very important. Mm-hmm. Okay. Part B and part C. Is that example 22 or example 23? 24. Ah, yes, okay. You didn't understand part B or part C. Trapezium rule is very, very simple. So they used to teach it in AS, but they got rid of it in AS for some reason. They got rid of a lot of things, honestly. It's shocking. Moved it around for year 2. I don't understand why. Anyways, the trapezium rule, the formula looks very intimidating, but it's actually really not that bad. So it's a half h, and then you got y naught, and then you got 2 plus y1 plus y2 plus whatever, right? Up until yn minus 1. The formula's nasty, okay? I'll give you that. But one thing that you need to appreciate is the most difficult part about this formula is remembering half h. Because if you just remember this as the starting value, and you remember this as your ending value, and then you think of these values as being in between, I'll do in between in black or something. You'll never go wrong. So the trapezium rule is, okay, let me get my y value, add it with my x value, and then add it by 2 times by everything in between, and then times that by half of the width. Then I'll get my answer. That's it. And I'll demonstrate this. So h is just the strip width, by the way. So that's not that bad. So h is given by the formula b minus a all over n. I don't think you need to worry about the formula because, well, it's just intuitive, right? If I told you this is my starting value, this is my ending value, I want to split it up into 4 strips, you can easily calculate what that would be. You don't need a formula for it. So I think it's ridiculous. And also, if you look at the table and how the values incrementing, well, you have to be a bit careful. It usually tells you what h is sometimes. But you have to be a bit careful. So 1 second. I didn't actually copy out part A and part B. Okay. So let me just copy the table out so I can't be bothered to sub values into a calculator. Although I probably will have to at some point. Okay. So this is the table, right, that you get. So in part B, let's say use the trapezium rule with all the values of y. Okay, that is interesting. Wow, okay. Now, I'll be shocked. So if you were to think about this table, there is, okay, no, actually makes sense, yeah. So they're splitting it up into equal strips, right? So basically, if you add pi over 12 each time, so if you add pi over 12 and pi over 12, you get pi over 6. If you add pi over 12 3 times, you get 3 pi over 12. That's the same thing as pi over 4, right? So the whole point here is the h value is just pi over 12. Do you understand? If you want more clarity on why that is, by the way, take the ending value, pi over 3, take the first value, 0, and then see how many strips there are. So there's one strip between, one strip between this, that's 2 strips, that's 3 strips, and then that's 4 strips. So it's just, pi over 3 minus 0 divided by 4. Does that make sense? So you're splitting up into 4 strips. You can also think of that as, pi over 12. Is this making sense? Can you see there's 4 strips? So you understand h is equal to pi over 12, yeah? Okay, so now we know h. That's probably the most difficult part of the question done. You have a half times h, which is pi over 12. And then you can start putting in your massive brackets. So remember what you do. You take the first value and the last value. You add them together, okay? Or, what you can do is just remember it like this. You can think of it as the first value plus 2 times all of the values in between. So you're going to do plus 2, and then you're going to put brackets 1.035 plus 1.155 plus 1.414. Okay? So you're multiplying all of the values in between, and then you're adding that by 2 at the end. Does that make sense? So when you do the trapezium, you just have to remember, as a rule of thumb, you add the first value, the last value together, and then you add all of the middle values times by 2. But actually only times the middle values by 2. That's it. You can say the first value, add 2 times everything in the middle, everything in between, and then add it by the last value. And that's it. That's it. That's all the trapezium rule is. That's not that bad, right? So don't forget that. And then you get an answer if you plug that into your calculator. And that's it. So you would get an answer of 1.34, they say? Yeah. And they say, explain with a reason whether your answer in part B will be an underestimate and overestimate. This is actually a very interesting part. So the trapezium rule is concerned with splitting up the area in between this curve and this x-axis, and actually this line, I should say, pi over 3, into distinct trapezium. So if you were to think, okay, let me split this region up into 4 separate trapeziums. Incorrect. It's actually over. Because if you were to think about drawing trapeziums, and I should probably, give me a sec. Let me make this more distinct. Let's say that's the y-axis. Let's say that's the y-axis. Let's go to. Draw a trapezium between each of these points. So basically, if you look at the tips of each of these points, including this top bit here, if you look at the trapeziums, notice you got these little gaps in between. So it's actually overestimate because you're only looking at the area of the blue region, but notice the area of the blue region is actually, there are portions of it which are underneath the trapeziums, right? They don't have the whole trapezium. So it's actually, the answer is overestimate. Does that make sense? Because of these gaps. I think, oh, actually, they have this thing here. So it says, if f of x is convex, don't listen to this. Just don't worry about this. On the interval, then basically the whole point here is when you think about a curve. If I was to give you two separate curves, give you this curve, and then like give you this curve. Okay, that's better. And if I asked you, use a trapezium rule to estimate the area between this point and this point, well then, if you imagine connecting straight lines across, can you see that the trapeziums, they're a bit higher. They're going a bit higher than they should, right? They're accounting for this in this area. So that's an overestimate there. But then if you look at this curve and then do the same thing between, like, say these 2 points, that's a triangle technically, I know. Can you see you're missing bits of the curve? So you're not accounting for that region, that region, that region. This is like missing. So this is an underestimate. But I guess the idea of the fact of it being convex and concave makes sense, because if you look at this curve, remember, because it looks like a cave that you would enter, a tunnel, then we say it's concave, right? Concave because it looks like a cave. But then, you look at this curve, it's convex, yeah, because it has to be, it doesn't look like a cave. So does that make sense? That's basically what they're getting at. I don't know what the reasoning they give was. Do you know what? I kind of respect what they're saying. I completely respect what they're saying. Because how else are you going to justify your answer? If you say the graph is convex, you're completely justifying your answer. So if the graph is convex, then it's an overestimate. If it's concave, then it's an underestimate. That's a good point. I think if you want to justify your answer and you could think of a reason, then just say the graph is convex. Probably not. But I mean, it gives you a flow to your answer. It's like the main point. Graph is convex, so the lines connecting the two endpoints. Lines connecting two endpoints would be above the curve. Okay, right. Yeah, so what they're saying is, if you were to take any two endpoints and then connect a line between them, note it's above the curve. That's it. Do you see my point? Any point on this line is above the curve, basically. Yeah. Okay, do you have any questions? Okay. Yeah, well, I'll give you some questions to practice for integration. I started to realize you're moving quite quick now. Just thinking it's actually just end of October now. It's good. Of a differentiation integration trade. I think you should be fine now. Pretty much in a very good spot. And you've done majority of mechanics, even though you've not done it in school. It's very good. You're in a very good spot. I mean, ideally you want to have finished everything by now, but it's still very good. Yeah, I remember I told you by August. That never happened. Yeah. I mean, of course, I said to you like a couple of months ago, it would be ideal if you did some self teaching or self reading on Pure, and I would help you with mechanics basically. So yeah, it's fine. You did some bits. So that's better than nothing at the end of the day. So it's good, but yeah, it's not a big deal. But it puts you in a very good spot. What I'll do is I'll send you some questions on integration because you pretty much finished it now, technically. Just need to do separation of variables, and that's it. No, it's not simple. It's similar to rates of change. Just give me a second. I'll give you some questions to do on fast chain looks not bad. Do that, could do that. Oh, very attractive, very attractive. Let's have a go at. I'm very reluctant, actually. Do you remember the section in the textbook on reverse chain rule? It's 11.4, I think. 11.4, 11.5. Yeah, so make sure you thoroughly go through that section. I mean, thoroughly. Very important. Very, very important. No. But it will help you with really difficult questions, which will probably come up. Which is why I suggest. Just give me a second. Okay, so you choose. Do you want to go through by part? Do you want homework on by parts? Do you want it on reverse chain rule, or do you want it on substitution? It's between those three. Yeah. Okay. So the homework will just basically do 2, 3. It's Thursday today, right? It's Saturday. I think you should be able to do the first 1, 2, 3, 4, 5 questions. Okay, do the first 4 questions for homework, and then we'll go through the rest. Yeah. Very good questions there. The first 4 questions are not too difficult. Can trip you up, but they're nothing too challenging. The rest of the questions, they do get quite difficult, but it's very manageable. Very manageable. Okay, yeah, you don't have any questions, do you? Okay. If you don't have any questions, then I'll see you on Saturday, okay? No worries, take care, bye.